In the previous video, we looked at two examples of trickier epsilon delta proofs. Well, not actually the proofs, but their setups. So here's another very tricky example, but once you understand how to do this and the methods involved, any epsilon delta proof that comes your way with rational functions and inverses will be just a breeze. So let curly f of x be defined as curly f of x equals x over 1 minus x squared. Now, future journeys into calculus, you might see this function again somewhere in a very unusual way, which corresponds to why we have a curly f here. If you might guess why, let me know in the comments. Now, it's equal to x over 1 minus x squared. Using the epsilon delta definition of a limit, prove that the limit as x goes to 1 of curly f of x is equal to negative 1. So indeed, if you plug in this equation 1 over 1 minus 1 squared, you get, this is going to be 1 minus 1 is 0, and you have negative 1, which is equal to negative 1. So that makes sense. So now let's begin the proof, or at least a setup for it. Again, we're going to always start with let epsilon greater than 0. And by the way, if you do not know how to set up epsilon delta proofs and how to do those, I suggest you look at other videos on this channel explaining how to do those in clear ways. So now we're going to find delta greater than 0 such that, and now you know the drill, we're setting up the inequality. We're going to say that x minus 1 is going to be in absolute values less than delta, which verbally means x is within delta of 1. And that implies that x over 1 minus x squared minus negative 1 will be less than epsilon. Now, of course, this will just become a plus 1, like this. And now we're going to do the situation where we kind of just find the lowest common denominator. And because we have a plus 1 here, we really don't have an issue with that. We can just rewrite that as the fraction 1 minus x squared over 1 minus x squared, excuse me. And now we can further characterize this as x plus 1 minus x squared all together under 1 minus x squared. And that is going to be less than epsilon. Now these x's, of course, cross out, and you get 1 minus x squared over 1 minus x squared in bars is less than epsilon. Now, of course, 1 minus x squared is the same thing as saying negative and then swapping the two places. So you get negative x squared minus 1. And if you know absolute value rules by now, the idea of absolute value of negative y equals absolute value of y, which again, for example, the absolute value of negative pi will be equal to the absolute value of pi. So we can basically get rid of this negative sign here just like that. And that's the one cool thing about epsilon delta proofs, that they're actually a lot more simple than they seem. And there's things like this with absolute values that you're allowed to do. So x squared minus 1, as you can see, is also a difference of squares. So you can factor this further into x minus 1 and x plus 1. And now we can split it, these bars into each individual component. So we get x minus 1 times x plus 1 over 1 minus x squared is less than epsilon. Okay, now the good news here is that we found our x minus 1 inside, but the bad news is that we still have these big expressions. Now the problem with this is that you cannot say that 1 minus x squared is going to be positive, because clearly it's not. It's going to be negative. So we don't know how to properly bound that. So what delta should we use to bound both this and x plus 1? Can we use less than or equal to 1? Well, that might be your first thought, but let me tell you something important. You cannot do that, because consider the function x over 1 minus x squared. Do you know if it's really defined well in a neighborhood around 1? How do you check that? Because you don't know what this function looks like, and I don't. But let me tell you something. If we set 1 minus x squared equal to 0, we can plug this into the quadratic formula, or just say x squared plus x minus 1 equals 0, and then put it into the quadratic formula, because we don't like to have negatives. And what you end up getting is two solutions. You get x is equal to negative 1 plus root 5 over 2, and you get x is equal to negative 1 minus root 5 over 2. Now, these are actually the golden and silver ratio, but they're opposites. So 1 minus root 5 over 2 is the silver ratio of psi. So this is equal to negative psi. And then this is equal to negative phi, as it's called, the golden ratio, 1 plus root 5 over 2. Now, what is this? Why is this problematic? What does this have to do with delta less than or equal to 1? Well, let me explain. Psi is approximately negative 0.618, which means that the negative of that will be positive. So negative psi is about 0.618, which is less than 1. And since this is a root to this equation, that means that at x equals negative psi, we're going to get 0 on the denominator, which means it's undefined, which means we cannot use delta is less than or equal to 1. Now, the good news is that we don't have to worry about negative phi, because negative phi is about negative 1.618. And so we can say delta is less than or equal to something that's less than that negative psi. So what can we do? We can say, for example, delta less than or equal to 1/3. All right, and I'm going to use 1/3 for a reason, because it's usually an unconventional thing to use. You could have used 1/2 perhaps, but I wanted to show you how this is going to work. With this initial condition, with x minus 1, you can see that negative 1/3 is going to be less than x minus 1, which is less than 1/3. Now we can generalize it into x by adding 1 on all sides, or 3/3. So we end up getting 2/3 is less than x is less than 4/3, right? And so now what we can do is we can reproduce this same inequality multiple times and do different things to it to basically get our result here of this crazy looking function and kind of inequality. So let's start with x plus 1. So let's take the x plus 1 case, and what we're saying is that we want to find x plus 1 in this inequality. And how can we do that? Well, by reproducing it here and adding 1 to all sides, we get 5/3 is less than x plus 1, which is less than 7/3, which means that the absolute value of x plus 1 is less than 7/3. Simple enough. So we can box this right now and circle it here, because we took control of that. Okay, now we're left with the 1 minus x squared. This is tough because this is a square term as well in the denominator, and it's an inverse. So we're looking for 1 over 1 minus x squared in absolute values, don't forget. So what we're going to do is we're going to take that same x inequality here, the general x inequality, and we're going to do different things to it. So for example, we can square it. And when we square it, we get 4/9 is less than x squared is less than 16/9. Okay, and now we can take the negative of that, and so what we get is we get negative 16/9 is less than negative x squared, which is less than negative 4/9. Okay, now we can take this same x and we can copy and paste it again, because we're going to have to be adding these inequalities together later. So taking the negative of that, we get negative 4/3 is less than negative x, which is less than negative 2/3. All right, and now we can add these two inequalities together, because if negative x is less than negative 2/3 and negative x squared is less than negative 4/9, then these two terms' sums should by logic be less than the sums of these terms, and that also applies to the left-hand side. So adding them together, we get negative x plus negative x squared, which is minus x squared. This will be in between. Negative 4/3 is going to be the same thing as saying like the 16/9, right? So you have negative 4/3. Oh, sorry, not 16/9. Whoops. This is going to be the same thing as saying negative 12/9, right? And then negative 2/3 will be the same thing as saying negative 6/9. So adding them together, negative 16/9 and then negative 12/9 is going to give negative 28/9, right? And on the right side, negative 6/9 minus 4/9 is negative 10/9. Okay, now we're close because we also want that 1 here. So all we have to do is just add 1 to all sides. And so if we add 9/9 to both sides, we get negative 19/9 is less than 1 minus x squared is less than negative 1/9. And now what we want to do is we want to take the inverse of this, because we want that 1, right? The 1 over. So if we take all the 1 overs here, we end up getting that negative 9 is less than 1 over 1 minus x squared, which itself is going to be less than negative 9/19. Okay, now, what do we make of this? We can basically say that 1 over 1 minus x squared, because it's less than negative 19/9, well, this is a negative, so if it's less than that, how do we make the absolute value out of that? Well, we don't. Instead, we use the left-hand side, which means that 1 over 1 minus x squared in absolute values is less than 9. Why is that true? Because if it's less than negative 9/19, then it's also less than 9, right? And it's also greater than negative 9, our other bound. Okay, the basic takeaway here is that we took a bunch of the same inequality of 2/3 less than x less than 4/3, and we reproduced it multiple times and did different things with it. We squared it, we made it negative, we flipped signs, we took inverses, because we did everything we could to try and reproduce that top expression here. So let's put it all together now. That means, with all of our work so far, that x minus 1 in absolute values times x plus 1 over the absolute value of 1 minus x squared is going to be less than what? Well, remember, 1 over 1 minus x squared is controlled by a 9. The x minus 1 is controlled by a delta. And then x plus 1, as we see over here, is controlled by a 7/3. So it's controlled by 7/3. Now, of course, we can take this and this, and we can get a 3. So it's going to be equal to 21 delta. Okay? And that's also going to be equal to our epsilon, right? So therefore, I'm scrolling around a lot, but therefore, triple dots, choose delta to be the minimum value, right? Because don't forget about that 1/3, of 1/3 and epsilon over 21. Because if 21 delta is equal to epsilon, then delta is equal to epsilon over 21. Okay, so this is your setup. And we can put a box around that, because when you do the proof, you'll say let delta equal to min of 1/3 and epsilon 21st. And you'll have a couple cases. When epsilon is greater than or equal to 7, right? That's going to be the 1/3. You choose the 1/3 as the minimum. And if it's less than or equal to 7, or if it's less than 7, I mean, you pick the epsilon over 21. So that was our tough example. But again, the main takeaway, and this is the trick that many people miss when they do epsilon delta proofs, that you can be fairly loose, honestly, with your inequalities, with the amount of times you reproduce them, and with the way you square them. Just be careful with the negative signs and the inverses, and be careful with the rules of absolute value. Okay? But apart from that, reproducing the same inequality multiple times and experimenting and doing different things with it, like squaring them and this and that, this will allow you to put them all together again in terms of delta and find a way to express delta in terms of epsilon. So I hope you learned something new here. I hope you understood the caveats behind selecting delta less than or equal to 1, because that's also very important, and how that root of the that causes the actual equation to be undefined will not allow delta to be less than or equal to 1. You have to pick a value less like that. So, for example, 1/2 or 1/3. All right. I hope you learned something new there. Thanks for watching. Come back next time. Till then.